We're going to talk about air now, and in doing so we're going to introduce many chemical concepts early on in the course. When we talk about the atmosphere, we're talking about molecules of air, and we may ask ourselves, why do they stick around? Well, you and I and the molecules of air all experience an attractive force that pulls them towards the center of the earth. When an apple comes loose from its place at the top of a tree, gravitational attractive force causes it to be accelerated towards Earth, increasing in speed as it goes. The atoms and molecules of the atmosphere also experience a gravitational acceleration, but because they have such tiny masses, their thermal energies of motion override the gravitational forces, and luckily the atmosphere doesn't just pile up in a thin layer at the Earth's surface. We do have a heavy load of air molecules on top of us at all times. We don't notice this because we're used to it. The atmosphere, as you might imagine, is an extremely complex system. Its temperature and pressure changes over a wide range of altitudes, and is bombarded with radiation and energetic particles from the sun. This barrage of cosmic energy has profound chemical effects, especially on the outer reaches of the atmosphere. Perhaps you've heard of the ozone layer. That is a very important strip at the top of the stratosphere. At the bottom of the stratosphere, which absorbs many of these very harmful high-energy UV radiation. There are three regions in our atmosphere, as you can see. The troposphere is the region nearly all of us spend our lives. Weather, quote unquote, all occurs in this region. And this troposphere goes up about 7 miles, that's a long way, and contains 75% of the mass of the entire atmosphere. At its top is a calm air area where planes like to fly. The ozone layer is situated at the bottom of the next layer, the stratosphere. The stratosphere contains about 24% of the mass, the weight of the atmosphere. There's no sharp physical boundary between the layer. It is actually a temperature differential that determines the boundaries. And these boundaries are important because gases mix very slowly between them. For example, pollutant gases generated in the troposphere find their way into the stratosphere very slowly. And this ozone stays in the stratosphere. In fact, ozone at sea level, or where we live, is very harmful to us. It is an irritant to our lungs. The mesosphere is way up there. That starts up about 30 miles up, and it's the top layer. And they figure it extends about 42 miles. That, of course, is, not a hard stop. There are fewer particles per volume as you go up, and the mass of the air decreases. So the pressure decreases until the atmospheric molecules simply fade away into almost perfect vacuum of outer space. This is just kind of interesting because sound is a compression wave and needs material to travel along. For example, air or water or earth. There is no sound in outer space, and which kind of makes it funny when you watch Star Wars and other movies like that, and you hear the whoosh of the huge space shuttles coming at you. But it sounds better, I'm sure. So what's in a breath? Oh, well, many things. It's a mixture. Primarily it is nitrogen and oxygen. Other gases, although present at very low concentrations, can have a major effect on our environment. As you can see, there are a number of ways we can show how each of the components, that is the stuff that makes up the whole, can be expressed. We call this the concentration. There are graphs we can use. For example, we've got the pi graph over here, and to the left, this is called a pi graph. A pi graph, and I'm sure you've seen those. And the other is called a bar graph. Both of them are very useful for quickly visually seeing how different components fare, how they relate to one another. And you can see by far nitrogen is our biggest component. He is pretty inert though. He does not react with much. Here's the player. Oxygen. Oxygen is what maintains living organisms. Oxygen is what is the major component of most minerals, the oceans. Oxygen is ubiquitous. For us, it is more useful to look at the actual numbers. Here we're looking at percentages of inhaled air and exhaled air. Percentage is parts per 100 total. So for example, when I say that nitrogen is 78%, it means I've got 78 particles of nitrogen over 100 total particles of air, of the mix. Okay? And when you add up percentages, they should all add up to 100, or the total. And we work with percentages all the time, often when we're looking at sale items. Yes. Okay. We have other things besides oxygen and nitrogen, something called argon. And argon is a so-called noble gas. He doesn't do very much. Look, you inhale him, you exhale him. Your body does nothing with him. His name is lazy because he likes to hang out by himself. He doesn't like to interact. He doesn't like to do much. Carbon dioxide, you might have heard of. This is a major product of our bodies. We take in oxygen, we use oxygen. Believe it or not, we use I'm not sure why this isn't exactly 78, because our bodily functions don't use nitrogen from the air to any appreciable amounts. But it is oxygen in our lungs that is taken throughout our body that makes us work efficiently. Okay. And water. Water is a very high percentage of what we put out. In fact, these two are products of metabolism. So how do we report concentrations of trace components? These are really, really small amounts. We're going to find that some airborne components in the parts per million, parts per billion can be important and harmful to us. But first off, let's look at carbon dioxide. Now it's said on the other side that it's 0.04. The actual amount's 0.0385. That's how much it's usually measured. And that means there are 0.0385 molecules of carbon dioxide in 100 molecules of air mixture. More useful is to try and get a larger sample size than 100 molecules. How about we use 1,000,000 or 1,000,000,000? Can you think what would happen to the number of particles? It's going to go up. The actual number. It is going to be bigger than this 0.035 because we have a bigger sample size. We can show, in fact, that this amount as a percentage, okay, is equal to 0.385. Notice we've lost the 0 per 1,000 parts. So I've used a 10 times larger sample size. I can also show it's 3.85 per 10,000 total parts. Now these are the total parts here, okay? And then keep going, the same idea, you get the idea. And finally, this is what is usually reported in parts per million. I have multiplied by 10,000 my sample size. And I can find that this is a much easier number to report than this one. This is parts per 100. This one's parts per million. Okay, let's convert the concentration of argon in air from percentage to parts per million. Pull out your calculators and do it with me. In the first table, we were told that the amount of argon is 0.9%. Yeah, argon. Let's call him AR just for shorthand notation. We're going to find out it is appropriate shorthand notation, in fact. Okay, and this literally means I've got 0.9 less than 1. Okay, that's a 9/10 of 1 molecule. Remember, this is a relative amount. So don't get worried that it's not a whole molecule or a whole atom. Okay, it is 0.9, and in this case it's pure atoms, so I'm going to put atoms of argon in 100 particles. Yeah, let me use particles so I don't have to differentiate between the actual structure. In 100 particles of air. So that means that's a mixture of which argon is a part. And we saw that so is nitrogen, so is oxygen. Okay, now let us express the same quantity in parts per million. That would be particles of argon in a million total particles. The two values will be equal. What am I talking about? I'm saying that the relative number of argon particles must be the same in each. Remember I said relative. So the concentration of argon particles must be the same. It won't be the exact number because I've got a different sample size, but the relative number. All right. Let's use a proportionality factor. We can say X particles of argon per million particles. And you can see I'm going to start changing from writing these long numbers here into something that is very useful called scientific notation. We scientists are a lazy lot, and so we have a lot of shortcuts. And this is got to be equal to 0.9 particles of argon. I'm not adding or subtracting any argon, right? In 100 total particles. Okay. So let's solve for x, which means let's isolate x by itself. To do so, we multiply both sides by a million. And if we do that, we find that we can, let me do it quickly over here, particles argon over 1 million total times 1 million equals 0.9 particles of argon over 100 total times a million. If we do the same thing to both sides, we are in good shape. It means we've multiplied by 1. If I brought this side over and divided it, you'd see that it's a million over a million, which is 1. So if we do the same thing to both sides, we are cool. Okay, now if we do it over here, we can cancel because it'll be a million divided by a million. When you multiply, you are doing it to the entire quantity here, right? Now what happens here? Well, let's pause. I divide 100 down here I divide 100 by a million, a million by 100, and I end up with x particles of argon equals 0.9 particles of argon times 10,000. That is a million divided by 100, and I come up with 9,000 parts argon per million total. Per 1 million. Oh, let's stop this. Okay. Cut it out here. Let's go here. Okay. We're going to start back up here. Okay, start again. All right, so we have 0.9 parts per argon divided by 100 total parts, that's my percentage, times a million. And a million divided by 100 is 10,000. My total then if I wanted to know how many particles of argon in a million would be 9,000 or 10,000 times 0.9. So we've got 10,000. And we usually write this as ppm, parts per million. If I wanted to know parts per billion, I multiply by 1,000. Okay, this is called using a conversion factor when we change from parts per hundred to parts per million. It is converting from one unit of measurement into another. And we do this all the time in chemistry. We take the original quantity, multiply it times a conversion factor, and get the equivalent quantity in a different set of units. A conversion factor is a fraction. It means I've got a numerator and denominator, and they're the same quantity expressed in different units. So that may not make sense to you, the words, but you do this all the time. For example, we know that 12 inches and 1 foot are the same length. That means they're the same quantity, but notice I'm in different units. One is inches and one is feet. Let's use this, in fact, to find out how many feet are in 23 inches. I can write this as a fraction, you see. 12 inches, and I say it's 12 inches per foot. Okay, I can write this as per foot. That means I'm dividing by 1 foot. Or I can write the equivalent, 1 foot per 12 inches. And what I'm really doing, it's often called a unit analysis, because I'm simply using a factor of 1 because these guys are equivalent. Okay? All right, so 23 inches equals how many feet? Let's do it. 23 inches. And then let's multiply our original quantity by the conversion factor. Since we want to end up with feet, I need feet in the numerator and inches in the denominator. And then look, which one would I use? This one. Good. 1 foot is equivalent to 12 inches. So my answer is 0, and I didn't leave myself much room, did I? 96 feet. Now, if you did this on your calculator, you might have gotten something like 0.9588333 number. Now, this is very important because, again, you want to use a number that makes sense. Your answer should have the same number of digits. Same number of digits as your data, as your original number, as your original quantity. Or just your original data, okay? Which means I've got 2 here, so I should only have 2 here. And since this is above 5, I round up, and that's how I got 0.96. What if you've got more than one number? Well, your answer then should reflect the smallest numbers of digits. For example, if I multiplied 6.1 times 10.2, my answer can only contain 2 digits. And then it would be 62. And you can think of this as the process of the weakest link. My number here is only as good as my least precise or smallest number of digits data number. Okay. What about the conversion factor? Well, these are considered exact, are definitions. And let's call these exact definitions.